Anu, are you able to see the slides here?
I can see the title slide, yeah.
Okay, appreciate it. Uh, just take the slides. Okay. Hi, everyone. Welcome to the first reading group. Today's paper is Beyond the Buzz, a programmatic take on disaggregated serving. Today, we will first introduce what is a prefill and a decode, and then two prior solution, and then the ultimate solution of disaggregated serving, and finally introduce some considerations of PD disaggregation. So after this lecture, you will know how PD work and how you can get the most performance out of it, such as should you use it for prefill heavy workload or for small models or big models. We will discuss all these industry practices. Okay, so first, what is prefill and decode? In the prefill phase, it is taking in the tokens and then processing them together in a chunk. On the chart on the left side, it is a n by n computation. Why? Because the query is compressed of n tokens, it's n by d, and then the decode, the k, the keys, is also d by n. So the resulting attention is a n by n matrix, whereas a generate phase, the decode phase, you output one token at a time. So each time it is 1 by d multiplied by d by n. So it's 1 by n computation. That's why prefill is very fast, whereas decode is prefill is very slow, and decode is fast. How does KV cache come into play? After the prefill phase, you will get the QKV, the intermediate states of the context. So they are the meaning of each tokens. Each token has a K and V cache associated with it. And then we will pass this to the generation phase, which is the purple shade on the bottom right. It avoids recomputing the context. That's why it's called cache. As we have mentioned, the behavior is very different. Decode is very fast, sends only one token at a time, but prefill is very slow. Imagine if you have one machine, one GPU, in an online setting where there are constant requests flowing in. Should you prioritize the prefill requests first, or do those ongoing chat windows? Decode means when the chat is producing tokens one by one. So in a single step, if you can only choose one computation, which one should you prioritize? Is it the incoming one or the decode? Let me share the screen again. Okay. Slideshow. Yeah, so the question is, in this setting, should you prioritize prefill or decode if you only have one machine? If you prioritize prefill, what will happen? The ongoing chat, the decode chat will need to wait until a long prefill to be processed. But if you prioritize decode, the prefill will need to wait. The first solution is prioritize prefill. Why? Because many prefill comes in. How about just let the prefill come do first, and then let decode gradually process? But then the problem is, if the prefill is very long, such as 1024 tokens, all the ongoing decode requests will need to wait. So say user 1 had a ongoing session, and then comes user 2 that throws in a new chat. So user 2 will occupy your GPU, and user 1's ongoing chat will need to wait. So how to overcome that challenge? A great innovation is chunked prefill, which is now the default processing in VLLM, also SGLang. This is a good paper. It's also the piggyback prefill related technique. So what does it do? It caps the sequence length. The previous problem was if a prefill, say user 2's prefill is very long, user 1 in the decoding stage and user 3 in the decoding stage needs to wait. How about we chunk this prefill up? So instead of 1024, let's say the chunk size is 4 tokens. Then in one step, we just process 4 tokens at a time. And then in the second step, the scheduler can choose another user to do their decode. And then scheduler will return to user 2's long prefill. This way, the chunked prefill will avoid user 1 and user 3 waiting for too long. In addition, on top of this, there's a technique called piggyback prefill. What it does was, instead of processing only decode or prefill in one batch, we allow them to happen together in one batch. Previously, you see decode and prefill, the shape of the input are vastly different. So how can you batch them together? The chunked prefill or piggyback prefill optimize the kernel level to allow decode and prefill to happen in one batch. And in this way, say this prefill of user 1, user 2 is in this batch. You can also stuff some decode tokens inside in one batch. So in one step, you will get tokens for the user 1 and user 3, as well as processing the prefill for user 2. So now the problem is how to determine the chunk size. In this example, we use 4 tokens as a chunk. To process this 1024 prefill, we need a lot of chunks, which will incur overhead. So should you use a large chunk size or a small chunk size? Let's see what happens if we use a big chunk size. Say our input is 65K tokens, so a very long input. Let's say the chunk size to be also big, to be 32K chunk size. Then we just need 2 steps to finish the prefill, right? So now what happens if we have a big chunk size? Now the chunk is 32768. In this batch, we have user 2's prefill request, also user 1, user 3's ongoing decode. How long will user 1 and user 3 wait until they can get the next token out? They need to wait for this entire batch to finish, right? For the GPU to unleash the lock and give back the tokens to the users. If a big chunk size, generation speed will go up or down. It will go down. The decode will need to wait for the long prefill. Then how about let's use a small chunk size, say 16 tokens. Then every batch, the decode can output tokens very fast. The generation is happy. But what about prefill? Prefill will need to be chunked into multiple parts, so the prefill will be slowed down. What else? What about GPU utilization? Since the batch size is small, only 16, the algorithm intensity will go up or down. It will be drastically reduced, right? Since the matrix is very small, so the flops will go down and GPU will be unhappy. Very low throughput. So now what to do? Should you use a big chunk size or a small chunk size? There seems to be a trade-off, right? On the bottom right, the x-axis is interactivity, which is the generation speed. That measures the decode speed. On the y-axis, it is throughput. So how many requests you can process together. Therefore, the trade-off is if you use a large chunk size, you get very high throughput. GPU utilization is high, but your latency will suffer. Whereas small chunk size, the interactivity will be high, the generation speed is fast, but the throughput is low. GPU is underutilized. Is it that we will have to suffer this trade-off forever? Is there a way to push the Pareto curve outward so that you increase on both dimensions at the same time? This is today's ultimate solution, PD disaggregation, prefill decode separation, which is the heart of Dynamo. What is the idea here? Let's separate prefill and decode onto different instances, onto different GPUs. Since prefill is a n by n computation and decode is a 1 by n computation, why not use separate hardwares for those? However, if you were to design a prefill and decode system, what design choices should you make? How many prefill GPUs? How many decode GPUs? And in what situation should you have more prefill? And when should you use more decode? The first design choice is model partitioning. On the left, you have the prefill pool. On the right is a decode pool. For prefill, should you use, as for model partitioning, there is tensor parallelism. There's also pipeline parallelism. Should you use tensor parallelism on prefill pool or decode pool? Or should you use the pipeline on some of them? How to decide? And indeed, it makes a big difference. Only prefill, so prefill is only good for one of these partition methods. So let's dive in. So what does TP do? So tensor parallelism is spreading a big tensor into small tensors onto 4 GPUs. So each tensor will have less compute to do. So it will be faster. Does tensor parallelism improve throughput or latency? Since it makes each individual computation fast, and you do those together, it made the entire system fast. So it helps with latency. Therefore, tensor parallelism helps latency. And which phase needs latency? Decode will need a very low latency, right? Because you need token by token output. It's very latency sensitive. However, for prefill, should you use tensor parallelism or do pipeline parallelism? For pipeline parallelism, it improves throughput because previously you can only have say one request, but now you can have first request in GPU 1 and then move it to the second GPU on the second step. So GPU 1 is free to process the next request. And So in the pipeline, if you have 4 GPUs, in total, you can have 4 ongoing requests at the same time. So this improves the throughput by a ton. But the problem is, you see, passing each prompt to the next phase will require communication, right? So it increases latency. That's why in decode, where latency is important, we don't use pipeline parallelism. Whereas the prefill, it's more throughput oriented, so we use pipeline parallelism. So now a question for all of us. Should we use a big batch size for prefill or a big batch size for decode? For decode, so what does batch size do? If a small batch size, you can get a token out very fast. That's why in decode, we want a small batch size. Whereas in prefill, the bigger the batch size, the higher GPU utilization. You can chunk in one entire prompt at once. So you want a big batch size for prefill. Next, the second consideration is rate matching. This comes to the initial question of how many GPU for prefill and how many for decode. Good question. So what do numbers look like? Gaurav asks, what do the numbers look like for big batch versus small? Okay, let me go back to the PowerPoint. For a big batch, so a big batch means it's usually so a big batch, say, is like 65K tokens in this batch, whereas a small batch will be 16K tokens. Yeah, it's 16 tokens. So in the prefill, we want a very huge batch. So this way, GPU utilization is high. It's usually, so for prefill, how long does it take to process one batch? Usually the constraint is 1 second, whereas for decode every token, it's around like 0.1 seconds, but the numbers differ a lot. A great question. Feel free to ask any follow-up on the chat or raise your hand. So now it comes to the heart of the prefill decode design, which is how many decode instance and how many prefill instance to place. If you allocate a lot of prefill and only one decode, what will happen is that these guys produce a lot of KV cache, and the decode can only handle one at a time. So this queue will be very long and become a bottleneck. Therefore, we need to find a balance to perfectly match them. And what is the metric we need to measure? It's called this rate matching. So it's the throughput of prefill. We want the number of GPU of decode to match the prefill's generation speed. So to do this, first, let's fix a first token latency. That is how long you process the input, the context. And this is usually like 1 second, between 1 second to 10 seconds. Think about GPT. When you throw in a paper or an article, how long can you wait until it outputs the first token? It's usually like 1 second or 5 seconds, right? And you will get annoyed if it's too long. So GPT under the hood, it fixes a first token latency, say 5 seconds, so that you must give users a token within 5 seconds. So this constraint will determine the prefill configuration, right? Since if we have this target, we can use the pipeline parallelism and the number of GPUs to match this latency target. And then we will, after fixing, say, 4 prefill instance, so suffice for the 5-second target, we can then determine how many number of decode GPU to match the throughput of this 4 GPU in prefill. And the goal is to minimize the GPU count, to minimize the cost, right? And how to solve this? We sometimes use linear programming, but Dynamo has much more smarter ways to solve this. It's the SLA planner, which is very important. So now to make you become an expert in PD, should you use it for prefill heavy workload or a decode heavy workload? This is a important interview question. So should you use PD for prefill heavy or generation heavy? What does prefill heavy mean? It means the input length is very long. The input might be 16K input sequence length, and the output sequence length, OSL, output sequence length, is only 1K. In this case, it's called prefill heavy. So is PD good for these type of workload, or is it good for the reverse? Answer is it's good for prefill heavy. So why is it good for prefill heavy? Let's go back to this slide of the chunk size. So if it's prefill heavy, it means prefill will need a lot of prefill is long, so the chunk size needs to set very high. If you collocate prefill and decode, your chunk size is high, which will cause the decode to wait. So a long input means the more separation or more difference between the two type of workloads. Whereas if you are generation, if you are not prefill heavy, it's prefill light, the input is not that long over the decode, then you can batch them together easily. Whereas if prefill is much longer than decode, you can't batch them together. That's why PD exactly solves this prefill heavy workload. So what are some use cases here then? Deep research, and also RAG, retrieval augmented generation. Also like paper reading. Right? So deep research means synthesizing many articles and search results. So the input is huge. RAG is also having database of it. And that's why PD is increasingly useful in the modern workloads of those three. So is PD useful for big models or small models? This is a second key interview question. So how to think about this? On the graph, is it a big model or small model? On the left, this is the 8 billion. Middle is 70 billion. On the right is 400 billion. The blue line is the PD disaggregated serving, whereas the red line, the solid red line, is co-locating, which means non-separation using one GPU. For the 8B model, the improvement of blue line over red line isn't very drastic, whereas on the 400 billion model, the blue line is vastly big higher than the red line. It successfully expanded the Pareto curve, Pareto frontier. Therefore, the bigger the model, the more significant improvement that disaggregated serving can bring. Why? It's because you can use more parallelism strategies for bigger models. You are more flexible in your choice. So prefill, you can have like a TP of TP2, whereas decode, you can have TP of, say, 48. And only big model can allow you to have such a big tensor parallelism without being redundant. And that's why the bigger model give you more partition strategies. We have discussed, is it good for small input lengths or big input lengths? The answer is big input, because the longer the context, the graph, the more difference between the prefill and decode behavior. So if you co-locate, it's hard to pick a chunk size. Therefore, you must disaggregate to push the Pareto frontier. So if we fix the output sequences of 2048, only look at figure 1 and 3, you can observe clearly that when the input is large, the blue line of this aggregating serving is much higher than the co-located serving. When the sequence length is small, the improvement isn't very huge. Now, lastly, about rate matching. This is the most interesting part. Should you use, say, 1 decode and 2 prefill, which is the first case here, or the second scenario where you use 3.5 prefill and only 1 decode? The first is 1 prefill versus more decode. So which one should you use? It comes down to the traffic. If you are designing a Siri, a Hey Siri application, that will be latency sensitive, right? You want the real-time interaction. So the decode, you want it to be fast. In this case, tighter latency means on the x-axis, your latency requirement is very tight. So it's on the right side of the right axis. Say if you fix a latency requirement of 0.8, then is the green line or the orange line better? The green line is definitely better. And the green line refers to 1 decode and 1 prefill and 2 decode. More decode instances here. Therefore, for applications like Hey Siri, you should use more decode instance over prefill. On the other spectrum, say if you are to design an agent, then the latency isn't that sensitive. You can let it spin in the background for 30 seconds or 1 hour. But it needs to process a lot of input, right? The input length is long. A lot of context to do. So you need a high throughput to process those large contexts. So here, you will fix a line at the left side, which means the latency is not stringent. Then, which line performs better? Definitely the orange. And orange corresponds to 3 prefill with 1 decode. That means more prefill instance than decode. So if you were to deploy an agent system like a Chrome, a browser agent, or RAG agent, then you should have more prefill servers than decode servers. Now this is the last part of our presentation. What are some challenges of PD disaggregation? Say you want to ingest a paper, so you throw a 3-page article into ChatGPT. Even with the smallest model of 8 billion, the amount of KB cache after processing the context will be 3 gigabytes, 3 to 5 gigabytes. That's amount to a movie. And if you use Wi-Fi to download the movie, it takes 5 minutes. So can you wait 5 minutes for the KB cache to transfer from prefill to decode instance so that you can get your first token back? Can you wait for 5 minutes for that? Probably no. In the GPT, if you see that it waits a lot, then it means there's some problem with their PD disaggregation. And it's probably due to this transfer of KV cache. So how can we solve this problem? Or is it that PD doesn't really work? Although it sounds good in theory, but in actuality, you need 5 minutes for the KV to transfer. So what to do here? Is PD practical in the real life? And this is the paper of the title of the paper, Beyond the Buzz. So the solution, so this is a true problem. If you use Wi-Fi or even plugging in to Ethernet, the cable, you still need to wait like 1 minute to get a response. So the home Wi-Fi is 1 gigabytes. PCIe means the cable Ethernet. It's 200 times faster than Wi-Fi, but it's still slow for the KV transfer. Therefore, the only solution right now is to use NVLink. It gives you 14K improvement over the Wi-Fi baseline. And only with this can you transfer the KV cache from prefill to decode sufficiently. Because if you go to the 407 billion model, or even the DeepSeek of 671 billion, the KV cache of one request will be not just 3 gigabytes, but 10 gigabytes or 100 gigabytes. You need to transfer a huge amount of traffic between the prefill and decode instance. And that's why we need NVLink, not just 1, but 72, so that the entire cluster is orchestrated as one. How so you still might doubt that if KV cache get even bigger, say if the model is like 1,000 billion, will the KV cache grow to 1,000 gigabytes that even NVLink cannot handle? The good news is, even if the input length is very long, it's okay. The KV cache size grows with n, whereas the first token latency grows as n squared. What does that mean? So the input here is this n tokens. So the attention matrix is n by n. The compute, the algorithmic intensity is n squared. You need to wait n squared time for the matrix computation to finish. However, the KV cache, is it n squared? No, KV cache is only of size n because this K matrix is a d by n, where d is a constant. So it only grows with n. So k plus v is just 2n instead of n squared. Therefore, the bottleneck is at the compute instead of the KV. So the KV size won't grow that much. So you can transfer the KV easily without letting it to stall your first token output. Second, as we discussed, if a model gets super big, your KV cache will also be big. So will that be a problem? The good news is that, let's say, let n be the number of the attention heads. So the small model can have like 16 attention head, where a big model can have 128 heads. If there are n heads, the compute will scale as n. Whereas, what about KV cache size? It doesn't scale at all. Why? Because we have some latest technique called multi-head latent attention, MLA. Multi-head latent attention introduced by DeepSeek, and it's used more and more commonly. This KV compression means you only have one KV head with 128 query heads. So even if your number of heads grows to 128, your KV head is only one. This also applies to grouped query attention, which reduces the KV heads. Therefore, the KV size doesn't grow as the model size. Therefore, your KV size is within bound, and it won't bottleneck your entire compute. So can current data centers support disaggregated serving? If you use NVL8, you have this Pareto curve here. But if you use an NVLink 72, which means you have you can link together all, not just the end-to-end GPUs, not just the neighboring ones, but also cross-link all the GPUs together and get a super high bandwidth. So the more NVLink domain you have, the higher the Pareto frontier. So you get both throughput and latency. The last slide is what is the future, which y'all might be interested. Have you heard of CDN? CDN is Content Delivery Network, which is behind YouTube, Netflix, and all those cloud services. Say a YouTube video is uploaded in India, and you want to watch it in the US. Do you need to fetch overseas to India? So YouTube, they have a CDN, content delivery network, between India and US that cache those content in the overseas. So they will cache those videos here, and the US consumers can directly pull from those cache that are nearby to them. In the future, the network will be KDN, Knowledge Delivery Network. Why? Without KDN, say there is a news of today, Halloween news. Many users might query this news. So everyone's ask what's news about. The LLM will need to compute the KV of the news each time. They will need to process the same context. What if we just compute the KV states for this piece of news once and share it across all the users? Share it across all the users. How to do that? We will create a content delivery network, whereas all the informations, books, videos will only be computed once and stored in the cloud. This cache, this content delivery cache, is will distributed will distribute those KV tensors to each users, so the endpoint users don't need to buy expensive GPUs or waste resource to compute those contexts again. And that's the future of knowledge delivery network. What do you guys think? So finally, as a bonus, what to learn in the future. To build this content delivery network, you need first NVLink, you need to understand the networking protocol, and also Nixel, which is one of the Dynamo's invention. It's a layer, networking layer that can plug into GPU direct memory and also cloud storage. Very important and powerful networking layer. And then thirdly, learn Dynamo, learn how the each component work, such as Nixel, how those networking plugin works, how VLM collaborate, and how it produces KV cache, how it transfers the KV cache. Any questions? So this is the paper, Beyond the Buzz, a pragmatic take on inference disaggregation. Very insightful. The link is shared in the Dynamo group chat. And thank you for watching. Feel free to ask any questions.
Hi, could you explain how the SLA planner works? I think you mentioned it during the rate matching slide.
Mhm. Yeah, in a nutshell, it solves the problem of how many prefill GPU and how many decode GPU, right? So
Oh,
it has
yeah.
some algorithm. Uh, yeah,
Is it like a linear programming problem? Like, do you know how like the system works for like the rate matching thing?
good question. So linear programming in practice doesn't work so well because of fluctuating traffic. So SLA Dynamo uses a more fine-grained algorithm. You can check it out at the Dynamo GitHub. Um, yeah, because we are at time, feel free to ask any questions in the group chat if that's okay. Any other questions, Anoop?
Oh, my question was mainly just about the KDN thing you were talking about, which sounds really interesting. I was curious, like, do you see that tying into Dynamo in any way, or is it more of a separate innovation?
Yeah, the heart of Dynamo. So what is at the heart of Dynamo? It is the KV cache transfer. It's transferring how to effectively transfer from prefill to decode, and that's why the Nixel component beneath it is very important. Very important. Such as the KDN will also use the KV transfer, right?
Yeah, that makes sense. Yeah, thank you. This is a great presentation, I think.
Yeah, thank you everyone, and feel free to ask any questions in the chat, the Dynamo chat. Have a good Halloween.